everyone. In the previous class, we started our discussion on elastic stress distribution around the circular tunnels, and we were deriving those expression using the theory of elasticity, and we could do up to the application of the boundary condition at r tending to infinity. We are still left with few boundary condition at the tunnel periphery, that is at r equal to a. So, let us apply that and see how we can get the complete solution towards this problem. So, in case of this boundary condition, in the previous class we already substituted the boundary conditions which were at r tending to infinity, that we did earlier. So, now we have the other boundary conditions which are like at r equal to a, you have sigma r to be equal to 0. Now, when this sigma r is equal to 0, what is the expression that we are going to have is this, that is half Sx plus Sy plus half Sx minus Sy into cos of 2 theta, which was the expression for sigma r. Now, this is equal to 0, and as per the stress function approach phi, last class we derived the expression for this sigma r. So, that is going to be a upon a square. Why I am substituting a here is that because I am applying this equation at r equal to a, plus 2b plus minus 2c minus 6e a to the power minus 4 minus 4f a to the power minus 2 into cos of 2 theta. Now, as we did in the previous class, let us again compare the terms on both the sides of the equation. What we will get is half Sx plus Sy would be equal to a upon small a square plus 2b, and this is going to be equal to 0. I write this equation as equation 10d. We already had 10a, 10b and 10c with us from the previous class, and then you will have the next term which is this one, that is minus 2c minus 6e a to the power minus 4 minus 4f a to the power minus 2, this is going to be equal to 0, that is equation 10e. What will happen at r equal to a to the tau r theta? That is going to be at r equal to a, your tau r theta is also equal to 0, and therefore, what we will get from here is minus half Sx minus Sy sine of 2 theta, that is equal to 2c plus 6d a square minus 6e a to the power minus 4 minus 2f a to the power minus 2, and this whole thing multiplied by sine of 2 theta, and since the boundary condition is that this should be equal to 0. So, I just substitute it like this. Now, we have seen that the constant d is equal to 0. So, therefore, if I substitute d equal to 0, so here this term will become equal to 0, and what I am going to get is 2c minus 6e a to the power minus 4 minus 2f a to the power minus 2, this will be equal to 0. This equation will be 10f. Now, let us see from the previous class. I will rewrite these equations for your ready reference. So, we had equation 10a as 2b was equal to half sx plus sy. Then we have equation 10c as 2c equal to minus half sx minus sy, and from equation 10d we can write that a upon a square plus 2b is equal to 0. So, that is what is going to give me as capital A is equal to minus a square upon 2 into sx plus sy, because 2b is equal to half sx plus sy from this equation. So, I just substitute this equation here in this equation, and therefore, I get this expression of A. We know that D is equal to 0. Now, this 10E and 10F combined form, they will give me F is equal to half Sx minus Sy into A square, and 10F will be minus half Sx minus Sy minus 6e a to the power minus 4 minus Sx minus Sy will be equal to 0, and from here I will be able to get E as 1 upon 4 with a negative sign into Sx minus Sy a to the power 4. So, I write all these equations in a combined manner as equation number 11. So, here you see we have the expression for B in terms of Sx and Sy, expression for C in terms of Sx and Sy, and then A we can find out like this. D is 0. So, A, B, C and D they are known, E is this and F is this. So, all these constants which were arbitrary we could obtain in terms of these applied stresses at r tending to infinity, which are Sx and Sy. Now, we substitute this equation 11 to equations 9a, 9b and 9c and see how it looks like. Please do it very patiently, otherwise you will make the mistake. Sigma r will be equal to minus a square upon 2r square into Sx plus Sy plus half Sx plus Sy plus a box bracket and half Sx minus Sy plus 6 upon 4 Sx minus Sy a to the power 4 r to the power minus 4 minus 2 Sx minus Sy a square r to the power minus 2 into cos of 2 theta. Further simplification will give me sigma r as half Sx plus Sy into 1 minus a square upon r square plus half Sx minus Sy into 1 plus 3a to the power 4 divided by r to the power 4 minus 4 a square upon r square into cos of 2 theta. Write it as equation number 12a. Now, what will happen to sigma theta? This is going to be a square upon 2r square, that is sx plus sy plus half sx plus sy plus minus half sx minus sy minus 6 upon 4 sx minus sy a to the power 4 r to the power minus 4 into cos of 2 theta. Simplify it further and what you will get as the expression for sigma theta as half sx plus sy 1 plus a square upon r square minus half sx minus sy into 1 plus 3a to the power 4 upon r to the power 4 cos of 2 theta. This is going to be equation number 12b. Similarly, we can write the expression for tau r theta when we substitute this equation 11 to equation number 9c. So, this is what that we are going to get is tau r theta is equal to minus half sx minus sy plus 6 upon 4 sx minus sy a to the power 4 r to the power minus 4 minus sx minus sy a square r to the power minus 2 sin of 2 theta. So, on simplifying this, we get tau r theta equal to minus half sx minus sy into 1 minus 3 a to the power 4 upon r to the power 4 plus 2 a square upon r square into sin of 2 theta, and this equation will become equation 12c. Now, notice here that sigma r, sigma theta and tau r theta, these are the function of r, theta, a, sx and sy only. These are not the function of the elastic properties of the rock. So, what does that mean? That elastic properties of the rock is not going to influence these stresses? Physically, this statement does not make any sense. So, we know that strength of the material is given in terms of its UCS, its tensile strength and its shear strength. So, indirectly these elastic constants, they play a role through these strength characteristic. We will discuss about this in more detail little later in this class. Now, this strength of the material, it reduces as the size of the cavity changes. Stresses are equated to this degraded strength, and here the elastic properties indirectly come into picture. So, we need to be careful. Equation number 12 which we derived just now, these give the stress components for a biaxial stress field when the applied stress field at the infinity is sigma x equal to Sx and sigma y equal to Sy. Now, we take some of the special cases and see how the form of the equation 12 becomes for these special cases. So, when we have the hydrostatic state of stress, that means that Sx will become equal to Sy and say that is equal to P. And since it is incompressive in nature, so I am introducing a negative sign with this state of stress which is P. So, what we are going to get if we just substitute this equal to Sy in equation number 12, what we are going to get is sigma r would be equal to minus P 1 minus a square upon r square. Sigma theta will be minus P 1 plus a square upon r square. Tau r theta will be equal to 0. And what will happen to the boundary condition, that is at r is equal to a, sigma r will be equal to 0, sigma theta at r equal to a will be minus 2p, and tau r theta at r equal to a will be equal to 0. This means what I am doing is that r equal to a, just substitute r equal to a here, and obviously in this case it is going to be equal to 0 only. So, this is what that we are going to get, see 1 minus a square upon a square. So, that will make it equal to 0, this will be 2p and this will become equal to 0. So, this equation I will write as equation number 13. Now, I define a factor called stress concentration factor. This I define as sigma theta upon minus p. So, this is going to be equal to 2 at r equal to a. Please remember this, we are going to use this information while we plot the stress distribution around a circular tunnel. Now, let us take another state of stress which is the uniaxial state of stress, in which case I will have Sx equal to 0, that means the applied stresses in the x direction they are 0 and in y direction they have the finite value. So, in such a situation what will happen to sigma r? This will be equal to half Sy into 1 minus a square upon r square minus half Sy 1 plus 3a to the power 4 upon r to the power 4 minus 4a square upon r square into cos of 2 theta. Sigma theta will be half Sy 1 plus a square upon r square plus half Sy into 1 plus 3a to the power 4 upon r to the power 4 cos of 2 theta, and tau r theta will be half Sy 1 minus 3a to the power 4 upon r to the power 4 plus 2a square upon r square into sine of 2 theta, and I make these equations as equation number 14. Now, let us take few conditions. So, the first condition is at r is equal to a and theta equal to 0. So, if this was the tunnel, I had the directions of these axes in this manner, that is x is equal to that is the horizontal axis was representing x direction and vertical was y, and if this is what was the rock mass, so any point was there which was having the coordinate as r comma theta, and this theta I took in the anti-clockwise direction from the x axis. So, when I say r equal to a and theta equal to 0, this means what? R equal to a means it is here at the tunnel periphery, and theta equal to 0 means it is in the x direction. So, what I am going to get here is sigma r will be equal to 0. Just substitute this r equal to a. So, you see this term will become equal to 0 and this term will also become equal to 0, resulting into sigma r to be equal to 0. Then what will happen to sigma theta? Let us see. Substitute r equal to a here. So, this is what that you are going to get, half sy into this will become 2 plus half sy into this term will become 4, and because theta equal to 0, so cos 0 is 1. So, you are going to get this as 3 sy. The second condition we take as at r equal to a and theta equal to pi by 2 or 90 degree. So, when theta becomes equal to pi by 2 means this angle and it will be along this y axis. And when I say r equal to a means at the tunnel periphery. So, what will happen at this point to all these stress components? See here, sigma r will become equal to 0 again because r is equal to a and this term will become equal to 0. The sigma theta will be half sy into 2 plus half sy into 4, and this cos of 2 theta, that is cos of 180 degree, that will become equal to minus 1, and this will make it to be equal to minus sy. So, in this case your stress concentration factor is going to be equal to 3, while in this case the stress concentration factor will be equal to minus 1. So, here it is 3 in the first case, and in the second case it is equal to minus 1. So, here I have summarized what we discussed for the uniaxial state of stress, that is when there are no applied stress in the x direction and only in the y direction these stresses are present. In that case, sigma theta upon sy we have seen that it is minus 1. If the applied stress is compressive in nature, the resulting tangential stress at the crown portion of the tunnel becomes tensile in nature, because you see that the ratio of these two is minus 1. So, in case if I take this Sy to be equal to compressive, obviously with that logic this sigma theta will become tensile in nature. And we are talking about the tangential stress at the crown portion, because this was the value at theta equal to 90 degree or pi by 2. Its magnitude at this location would be equal to the applied stress Sy, which is in the y direction. Now, let us say that this applied stress in the y direction becomes more than the tensile strength of the material, which is represented by sigma t. What do we mean? That is, Sy is more than sigma t. Then what will happen? Stress is more than the strength in the same mode, which is in tension. So, this would result into the tensile failure of rock in the crown portion of the tunnel, which is theta equal to pi by 2, and this is one of the most critical condition as far as the analysis of the tunnels is concerned. So, one needs to be very careful about the stresses at the crown portion of the tunnel. So, we have seen that for hydrostatic state of stress, both the radial as well as the tangential stresses, they are all compressive in nature. We saw that the stress concentration factor was all positive in that case. But in case of the uniaxial state of stress, it is not only that the stress concentration factor at the periphery of the tunnel is 3 times the applied stress, but also due to the tensile stress condition in the crown portion of the tunnel, this uniaxial state of stress becomes most critical state of stress. So, once again here I have given for your ready reference that what do we mean by the crown of a tunnel and invert of the tunnel. So, if this is the tunnel and you have these axes like x and y, so here this theta we are measuring from this direction. So, when theta is equal to 90 degree, then this is what is the crown, and when theta equal to minus pi by 2, which is this point, this is going to be the invert of the tunnel. Now, the expressions which were given for these stresses using equation number 12, we have seen that these are independent of the elastic properties. What were those? Like E and nu. So, those expression for sigma r, sigma theta and tau r theta, they were not the function of these E and nu. So, this does not really mean that stresses are independent of the material behavior. What happens in practice is that with increase in the size of the excavation, the strength of the rock is influenced, and the properties, strength properties such as UCS, tensile strength and the shear strength, they degrade. So, from design point of view, these degeneration in the strength properties will govern the design of excavation. So, when those expression for these stresses, when they come out to be independent of the elastic property, that does not mean that stresses are independent of the material characteristic or its behavior. They come in this particular fashion as far as the design of those structures are concerned. Now, here whatever are the expressions that we obtained in the form of equation number 12, that is the expression for sigma r, sigma theta and tau r theta. So, the variation of those stresses have been shown here in this figure. So, this stresses, they have been obtained as a part of the stress concentration factor, and the radial distance has been normalized with the help of the radius of the tunnel. That is, this all the data has been presented in the form of r upon a. Let us have the detailed discussion about this. First, you focus on this particular part of the figure, that is at theta equal to 0. So, theta equal to 0 means that here it is this axis, here theta equal to 0. So, I have on this axis r by a quantity, and on the vertical axis we are plotting sigma upon Sy. Now, this sigma can be sigma r or it can be sigma theta. So, this plot is showing the variation of sigma r with r upon a, and this plot is showing the variation of sigma theta with r upon a. So, if you just take a look at those expression of equation number 12, normally at r by a equal to 425, this sigma r would work out to be equal to 0, and that is what we can see here in this figure as well. That is, when this r by a is to the tune of 4 or 5, this sigma r will become equal to 0. What happens to the tangential stress? So, in this case it is the vertical, and at infinity it must be equal to the applied stress Sy, and therefore, this sigma theta upon Sy should be equal to 1 when this r tends to infinity. So, in this case you see that here r tends to infinity means that I am taking that the radial distance is about 4 to 5 times the radius of the tunnel, and that we can consider for all practical purposes to represent the infinite boundary in case of the elastic situation. So, you see that at r by a tending to 4 to 5, this sigma theta becomes equal to 1. So, this is what that we get from those equation and has been represented in this figure. Please remember, these are the typical variation of these stresses at theta equal to 0. Then focus on this portion of the figure. See here, this is at the crown, which is at theta equal to pi by 2 axis. So, when you have r by a equal to 1, that means at r equal to a, that is at the tunnel periphery, you have sigma theta upon Sy to be equal to minus 1, and we saw that it is like in that condition, that is stress concentration factor was coming out to be minus 1, and that is what has been represented in this figure. And when it goes to infinity, that is when r by a becomes equal to 4 to 5, this becomes equal to 0, that is sigma theta is approximately equal to 0. In case of the sigma r at r tending to infinity or r by a goes to 4 to 5, this sigma r upon Sy, it tends to plus 1, you see here. So, this is how the variation along the crown it looks like. Now, this is the variation along the circumference. So, move along the circumference from theta equal to 0 degree to this is theta equal to 90 degree. So, this is 0 degree, then you have here 10, 20, 30, 40, 50, 60, 70, 80 and this is point is 90 degree. Now, take a look here that what happens at theta equal to 60 degree. And obviously, because we are discussing about this the variation along this circumference. So, r is going to be equal to a. So, this sigma theta will be what? This was the expression from this equation, that is Sy 1 plus a square upon r square plus half Sy 1 plus 3a to the power 4 upon r to the power 4 cos of 2 theta. This was our equation number 14, right. So, just substitute r equal to a and theta equal to 60 in this and see what is the value of sigma theta that you get. So, you see this is going to be half Sy, this will become equal to 2. So, multiplied by 2 plus half Sy and multiplied by 4 and you will have cos of 120 degree. We know that cos 120 degree is minus half. So, this is going to give me sigma theta to be equal to 0. You see that this is Sy and this will become minus Sy. So, they will get cancelled out. Now, take a look here 10, 20, 30, 40, 50 and 60. So, we just have its projection like this here and then take it like this and here you have the stress concentration factor. So, you see that corresponding to theta equal to 60 degree, you have this sigma theta to be equal to 0. That is how your curve is also giving you. Now, at theta equal to 0, you have seen that sigma theta upon Sy works out to be 3. So, that is what has been shown here in this figure. Theta equal to 0, have the projection and you go along this line and see this point. Corresponding to this point, your sigma theta upon Sy works out to be 3. So, this is how one can show the variation of these stresses all along the circumference, along any axis, say we have seen that along x axis or y axis. So, this is what that I wanted to discuss with you as far as the elastic stress distribution around a circular tunnel is concerned. We will see other aspects related to this topic in the next class. Thank you very much.